Let's give these guys a big round of applause.
Hi guys, so this is Hendrik, I'm Brian. We've been doing quite a bit of research in the field of LTE 4G. We actually started with a row of talks beginning of 2014, LTE versus Darwin, actually showing, the basic problems that are in the specs and did a few theoretical attacks. And now basically we are back with the practical stuff. We brought our little toy, our eNodeB in the front here. We wanted to put it up and have it running here during the day, but sadly our power supply needs at least 160 volts. It won't work on 115, so sadly that won't be happening, but we've got everything else in the slide. So, we two come from Germany. We work for eNodeB. We are security researchers and analysts. We do quite a lot of penetration tests. It's just a small company, so we've got quite a lot of time for research. Do quite a lot of interesting projects. And yeah, basically, all of us were using 4G. It's an interesting topic, so we just decided to have a closer look at it. 4G brings quite a lot of new standards, brings in new technologies, and as always, it's new stuff, so it might be flawed. And as said before in the LTE versus Darwin, we found interesting stuff like the great phrase null ciphering algorithm, even though encryption has to be enabled. And yeah, basically we'll have a look what exactly our eNodeB will be doing. So what we're talking about is actually a macro eNodeB. So it's not these tiny wincy home eNodeBs that you put on your desk in your home or in your office. We're actually talking about the real base stations that are outside in the field and in the streets. This picture actually comes from Down Flamingo. It's basically a portable base station by AT&T, as you can see. The physical protection, it's not on the picture, but the fence is actually broken if you go something like 2 meters to the left. And you can go in, and then you've got your classical 19-inch racks with locks on the side. And if you go back up to the village, get a few lock picks, basically you know how things go. What actually makes life really easy for us, so this is a basic 4G network. You've got at the top the S1 MME, which is the management plane, and the U at the bottom, which is the user plane. Nicely enough, the serving gateway at the bottom actually basically is a simple IP router. And all communication that comes in from the eNodeB into the backend network is normal standard IP traffic. So we don't have any magical signaling protocols anymore as we had in 2G. We can go in, we can use all our classical network attack suites and tools and have a close look at the whole thing. So, a little part from our former talk, you've got physical protection, nice sentences in specs saying like, you only need to use IPsec if the site isn't physical protected. That up there is physical protection number 1. This is physical protection number 2. This is actually in the hometown where I come from. I have to admit these aren't 4G base stations. The one on the right is an NSN 2G base station by, I think, the German operator E+, and the one on the left is by O2. So yeah, that's what we see, what physical protection is. So our basic approach, go in, get a base station. Where do you get it? You try to go for eBay. If you're lucky, you'll find one. Price-wise, let's say something like $100 for the main unit. So that's cheap. It's cheaper than some Cisco switch. Get the whole thing up and running and actually look what's on there. And the classical stuff, you buy something on eBay and just hope for configuration data and some real-life traffic. So the whole setup consists of the baseband unit, which is usually in the rack on the ground. It includes stuff like the power distribution unit and things like that, the stack of sensors. Then you've got the remote radio head, which usually are the big white boxes that you've got on the cell masts underneath the antennas. They basically just convert analog data which comes in via fiber into the actual digital data which then goes out via RF. Then you've got the antenna as said, and all these parts simply are interconnected. The power supply that you'll need is something like minus 48 volts. When we started with it, we actually thought about something like plus minus 48 volts, so something like a difference of 96 volts. Luckily, you just use a 48 volt power supply and just turn around the contacts. Then you've got minus 48 volts and everything will be running. The RRU you only need if you actually want to do real RF. So it's a bonus. We don't have it with us today. It's about 25 to 30 kilos. And yeah, it didn't quite fit into our luggage. So the most important part, of course, is the BBU. It's the baseband unit. It's the thing that actually does the logical work. So in the end, if you can see it, it's in the bottom of the rack. We'll have a few pictures on the slides later on. And you've basically got blades in there, so you put in an LTE blade, it's an LTE base station, you put in a 2G blade, and it's a 2G base station. So quite flexible. Some of them actually have a backplane, which means that you will need the whole metal case to be able to run the device. With our Ericsson base station, you just need a few wires in the front, so you can actually just buy the digital unit itself, and you can start working with it. Is it here? No, okay. Then, of course, as said, variants of the eNodeBs, we are looking at the macro cells, the real stuff outside, not just as the small stuff. Eventually, the nice thing about the eNodeB is that it's actually the termination point of most encryption. So the encryption between your mobile phone and the cellular network will end in the field at the eNodeB. On the other hand, all encryption from the backend that goes out into the field, which should be IPsec encrypted, will yet again terminate in the eNodeB. So you know IPsec client certificates, if you own a box, you own a client certificate, and who knows what can happen. So the quick intro to the lab. As said, you hit eBay. eBay sounds easy, but you will need a few little terms. We've got them in the bottom here. So for Nokia, the stuff is called a Flexi BTS. For Huawei, you'll be looking for a BBU, an LMPT, or a UMPT, or both actually. For Ericsson, you need the RBS, which is the 19-inch rack case, and then the DUL, which is the digital unit LTE, which is the logical part which will do the LTE. Or for Alcatel-Lucent, it's the MBS. Base station, power supply, connect everything. Quite a lot of the stuff in telco networks has magical connectors. So you might actually have to sit down, create your own connectors, or really need quite a while to actually get the correct cables. We luckily bought the overall box, so everything together in a set, so we were quite lucky with that. That's one of the first pictures. Actually, up there, it's a little post-it that one of our friends put on there, actually saying nano BTS. So kind of, just for the scale, the antenna is about 2 meters 20. So just the best thing to play with. And this is our final lab setup. So we've got our Ericsson up here. We've got 2 Huawei BTS that we're working with. And, you know, if you want to get started, I think all the stuff in the rack should be about 5,500 euros or dollars. So if you're lucky, you can go cheaper. Otherwise, you'll have to spend a little bit of money. So the Ericsson RBS 6601 and the DUL, that's the part that we'll be talking about today. If you look at it, you know, it's quite easy. You've got classical RJ45 sockets, so you just need Ethernet cables and you're up and running. You've got something like a GPS setup, which is used, you know, LTE base stations are self-configuring, so you can actually send a dog out into the field to actually put the base station up, connect a GPS antenna, and add DHCP on the other side, and the base station will get all its configuration data from the core network, and it's working in a few minutes. So you've got GPS on there. You've got the LMT, which is the local maintenance terminal, which basically is the port that you use to own a base station if you're lucky. And then you've got the TNA and TNB ports, which basically are the ports for the backend access. You've got the IDL, which is if you have multiple blades for different cells in the device, you interconnect them. And then you've got the ports, the A, B, C, D, E, and F, which simply are GBIC slots, actually just to connect the RRUs and for the RF. If you start with the whole thing, you do a sniff. You'll be seeing down here, we've got two VLANs, VLAN 2 and 3. One for the user plane, the other one for the operations and maintenance. And you can see the stuff will start talking up. So what do? You set up your box virtual machine at the VLANs, and you just, set up the IP addresses that it's looking for. I think it's actually looking for 10 IP addresses, something like that. And the moment when those IP addresses are available, you'll see SCTP traffic, which basically is the BTS trying to connect to the backend network to set up the RF link. So from that moment on, you can do whatever you want. You can start setting up your own emulated core network and really start attacking the base station.
Good. So let's start with the attacking part. So all we've done is just to that base station. So that is the one we bought on eBay, like Brian introduced, or we bought online. And that is one which have been in production, I think, 1 year ago, something like that. So it's a real in production environment, 2 years ago. So it was set up, I think we have seen it in the log files, 2012, something like that. And whatever, it was just removed from site. And now we have an example and to demonstrate how attacks could look like in real life. Fortunately, the config was not erased, so it's a one-to-one config like it has been in production. So how to do that? We have multiple layers we can do some attacks on. The first one is the signaling traffic, so all that traffic which is necessary to set up connection from a phone and to forward the traffic and so on. So there is one interface, that S1 MME, where the eNodeB stands in communication with that MME, which is the management server, and is always exchanging some control information. So that is the first one we can take a look on. Then there are some local maintenance interfaces, that LMT port. There are also some remote maintenance interfaces or other operational stuff like SSH traffic, whatever. So if the engineer don't want to go on site and plug into that that connector, there are also remote possibilities. In this case, the local maintenance interface was quite the same like the remote one. So everything what we can do with the local interface, we now can do with the remote interface. But there is quite more. And then, of course, because we have direct access to the device, we can do some physical attacks. So just remove the cover and take a look inside, for example. And we had to do that anyhow because we got the whole box. We had no credentials. So we tried to, our goal was to understand the whole box, how it is working. Of course, we want to have configuration access because we want to use it for our own purposes. And finally, because we are attacking it, we want to get root, so we want to extract maybe some binaries later to take a look on. Again, keep in mind it's a real base station, how it is like out in the field. So it's not a theory or a one configured from us. Good. Let's start with the transport interface. So that is the connection from the eNodeB to the provider's network, to the core. That connection is called S1. And as introduced by Brian, that is split up in the control plane called S1 MME and S1U. S1U is just for the user traffic, so that means your calls are forwarded via that interface. So for attacking, For us now, not that relevant, but if you have access to, of course, you can just access the calls or SMS, whatever, or the internet data, which is transported over that interface. Physically, it's the same cable, so if you are in a man-in-the-middle situation, you have access to both. The MME as introduced is the control interface. This time, if we just assign the IP addresses to our laptop as we have connected to the machine, there are a lot of hosts. For example, I think there are 6 MMEs configured on that machine, but only one of them has to be up, so it's just for availability reasons. If we now assigned on our laptop that IP address standing here on VLAN 2, we could see that the device is establishing or tries to establish a HTTP connection. That is that S1. There is a protocol behind called S1AP. But anyhow, that should not be possible. We should not be able to do that anyhow because the standards say that it is required to implement IPsec. So what we expected, as we have been connected there, is an IPsec connection. That is something we have seen on one of the Huawei devices, for example, so that is not that easy to get in, of course, but in this case, we can directly talk IP to it. Why is there no IPsec? There is one node in the standards, like here, displayed on 3GPP TS33401. That node means if that interface is trusted, for example, because it's physically protected, then there is no need to use IPsec. And obviously, our one was physically protected. That is the same for the control plane, but also for the user plane. So there is no difference. The whole security is based on the IPsec here. There are also some interconnections between eNodeBs. There, again, it's the same. Good. The same, again, is for operation and maintenance traffic. So it's a kind of Linux on the box. So there is an SSH, like we will see later, and that one should also be protected via IPsec. But here, again, it's not. Let's take a look to S1. So there is a defined protocol called S1AP. The S1AP is used to do all the necessary procedures to transport authentication information, to establish a bearer, so that connection from your mobile phone, to initiate handovers, and so on and so on. That one is implemented via SCTP, and you can see that for S1AP, SCTP port 36412 is used. That is exactly what we have seen in that first Wireshark sniff. Just to give you one example what is possible via that interface, here is a list out of the standards implemented for S1 but also for X2. X2 is that interconnection of eNodeBs. So from our eNodeB we can theoretically also talk to other eNodeBs. And we can talk to that management entity in the core network, or just try to compromise our eNodeB itself and affect the traffic anyhow. So we see here some functions like NAS signaling, that is the transport of authentication information, for example. We have some trace functions to just take a look where our mobile currently is. We also have a configuration transfer. That means the MME is pushing some configuration updates over that interface to the eNodeB, like changing the RSCN, the frequency, or, and so on, or just makes the cell louder. That is everything implemented because there is a so-called feature called self-organizing networks or self-optimizing networks. So the central management entity will talk with all eNodeBs in the country and will also make some load balancers and so on. So if there is a need or is there a black hole of, if you don't have a signal, then the power is turned up at the eNodeB automatically. Something like that. And that are these functions we can, over that interface. Because there is no IPsec, there is only one message we had to simulate to access that interface. It's called the S1 setup request, or setup response. So the eNodeB is sending that request to the MME. We assigned that IP address, and now we emulated that MME. We've written a short tool. We also will publish after the talk. It's called fake MME, which is just establishing the connection and making the necessary configuration to turn that one up. But it's not much necessary, so basically only that S1 setup request and maybe some configuration changes, so that configuration transfer. So what we have had now running is the eNodeB is up, and we have an MME simulated. Now we can start attacking. For that, again, we made a second script. It's a man-in-the-middle tool where we can inject our own S1 messages. So all that messages shown in that picture, we can inject. It's just an SCTP. You just need to man-in-the-middle that. Well, you just can use some Python script, and then we modulated some of that S1 messages to check if that is really working. Who is interested for you? We use the a fuzzing toolkit of us called Odyssey, which we used for spoofing of the messages. Some of the scripts are published on our blog. So we can do some scanning, we can do tracing of some UEs, and so on. That is the main purpose of that interface. Good. So that is the main connection for connectivity. But still, we want to be root in the device. We want to access the configuration itself. So we need some possibilities to push configuration, use the maintenance tools, and so on. That is over the ORM network. Here in our eNodeB, it's a different VLAN. It's VLAN 3. There are, again, a couple of IP addresses used for that. We just picked out one of them because that one was used for NTP, for example. So we just symbolized our own NTP server. That's also necessary because, of course, the eNodeB must have some timing information, otherwise the cell will not work correctly. So that's quite easy. Taking a further look to the interface, so we made an Nmap scan. Here you see the outcome. Quite interesting, of course, the FTP and telnet. So for a device from 2012 or something like that, I don't know if that is really necessary. But okay, they have SSH anyhow. But all interfaces work. So then we see a port 80, so a HTTP server, not HTTPS. But I don't know if you really need HTTPS on that connection. In reality, there should be IPsec again, right? And we have some higher range ports like that 8443 and that 56834, which are used for the maintenance tools we will show directly after here. So the maintenance tools are very interesting because that are used by the engineers if they are going on site, if they're on setup of the machine, for example, or if there is a problem. So for example, if there is a fault state of that base station, an engineer will come on site, plug into a maintenance port, and doing something, reconfiguring, getting log files, accessing the monitoring with some magic tool. That always depends on the vendor. In our case, that is also possible remotely, so via the transport network, but you can only also plug into the LMT port, which is just a different connector, and then you have also access to that, that interfaces and tools. Yeah, so that is where we first focused on to get access to the environment. If you go on the web server, so that port 80, you directly have a download option of that magic tool. So that's really great that they provided to us that way. Very nice. Unfortunately, it's only running on under Windows, so not that easy for us. But the most problem was that Java 1.5 was necessary. So we first had to install XP again. Thank you. Yeah, that was almost the biggest problem to us, to install Java 1.5 and XP. Okay, if we had that running, we could just connect. That was quite interesting because we started the tool and then we had access to some information like the radio frequency information and so on. So that is how the tool is looking like. So you have different views for different configuration parts, like the whole rack you're standing in, which fans so the fan controller is inside there. Some debugging information, some monitoring information, and you can also access log files like that one. And you see there are a lot of errors popping up, of course, because some other parts of that rack where that eNodeB was in are missing. But okay, you can just remove that part in your configuration and then it's working, so that's not a problem. More interesting is yeah, maybe you have missed that, guys. So again, in the standards, there's done something that that setting up and configuring the eNodeB shall be authenticated. Unfortunately, there was no password for that tool. So we just started that tool. Like here, you can you can set up an IP address, a name, and maybe a comment. Then you click on connect, and you are in. So again, quite too easy. The biggest problem was to just install the tool. Okay, so we had configuration access, but still we had no operating system access. The configuration is that one which the engineer is using. But furthermore, over that interface, there are some other services provided like FTP, Telnet, and SSH. That is where we also wanted to take a look on. But so we can also try some exploits on Java. So since 1.5, I see there is quite a lot. So that is also a good possibility to compromise the machine. In our case, it's unfortunately not asking for a password, so we can't do some password brute enforcing here. And if you connect with that tool, it's establishing a connection to the high range port I showed in the Nmap, so that 56,000 stuff. There it is establishing a connection via GEOP. So it's Java. I think Brian is saying something to that later. And over that interface, it's transmitting the whole configuration data of the BTS. And that is also not authenticated and secured anyhow. So there is no sequence. You can do replay attacks, whatever. You just need to know how that GEOP is working. It is just transmitting the configuration directly. So next look. That was also not that hard. There were two users configured on the system called RBS and Cello user, and the password for both was RBS. And again, we could log in via Telnet, via FTP, and via SSH. Okay, there were some outdated SSH keys used, so our system was prohibiting the connection first, so we have to enable that algorithms manually. But okay, then we are in and had access to the whole device. If you take a look to the file system, there was a lot of interesting information, like that path.w, so it's a kind of Linux you see here, where we can extract passwords again if there are other users configured, but usually not supported. But more interesting is that security CFG and that folder called IPsec. That's a folder where the IPsec keys are stored. So if you have access, you can just extract your IPsec keys here. So again, really, really nice because it's also possible remotely. Gives the attacker a lot of possibilities, right? Good. Then we had access to everything, could take a look to the local configuration and also to the local web server. The local web server was vulnerable to a couple of exploits because it, again, used a very outdated Java SDK, so 1.16. There are also some other ones, which Java applications running on, which are using some other outdated Javas. So there's a lot possibilities to compromise a machine. And the web server is just used to provide the element manager, which is an LMT tool, to download. And also some XML configuration is placed there. You can also directly access without any configuration. You just need to know the path. But you see, if you're starting the tool, you see in Wireshark. While we discovered the web server, we unfortunately had another vulnerability found here, just a DOS. But it was not a DOS of the web server, it was a DOS of the whole eNodeB. Because the web server is running with high-risk privileges in the operating system itself, so it crashed. While we scanned the machine or the web server with a crawler, the whole machine crashed. That's also interesting. Good. So far, we have taken a look to the to the configuration, to the operating system. And so we had some access to. Obviously, the whole machine was not wiped or erased by the provider. And obviously, no IPsec is used on that machine. But okay, even if it's used, you find a way to connect to and extract the IPsec keys. There are some kind of hard-coded or default credentials, like RBS or Cello user RBS. There is a possibility to change it, but I think it's not really used in. It was not that easy. And even the login with that element manager is working anyhow all the time. There is Telnet in use, also interesting, because you can just sniff the traffic then, and then you have the real credentials if somebody's logging in, and you have a lot of unencrypted maintenance interface. So what's running on? The eNodeB has an real-time OS running. So it's very, very plain, and it's it's all stored on a compact flash you see here. So if you just open the device, you have a compact flash in where the whole operating system and the file system is on. That's quite interesting. So there are just some problems here because it's not easy. It has an own file system which is based on gzip. So you just have to recognize that first. But the architecture is a PowerPC, so we expected to see there some PowerPC binaries, and the architecture is also assisted by some FPGAs and also one ARM processor to do all that radio stuff and so on. The flash disk. The first we removed that from our eNodeB and plugged it into our laptop. First, it was not that easy because it's a flipped architecture, so all that little endian, big endian stuff. We can see here in that binary, if we made an analysis, that alphabet here is just, it's flipped. So we had to switch that first to access the direct information like the powers PC binaries you see here. And then all the files here are gzipped. It's a small system, so it's an embedded system, so they just want to keep some space. Save some space. But now we had access to the upper layer operating system, could extract binaries and start with reverse engineering. And also, because we had access to that volume, we can again extract the IPsec keys. Good. Another interesting one, if you're on the machine just for debugging, you have some debugging interfaces enabled there, and you have a RAM log. And the RAM log displays the whole booting process. So if you want to do some attacking there, you can just hold the machine on the right places here. There are also some commands for that. And you see here on step 2 that it's mounting that gzip volume and powering up. And so that is our volume we extracted here. So we can just modify it. Just small joke for us is that line, that no magic found. That was quite funny to see that in the log file. Good. The rest is for Brian.
So, you go in and as said, there's configuration on there. You've got a mobile country code and a mobile network code actually defining an operator. Luckily, you found the numbers 311 and the MNC 660. Turns out it's an American operator, or an old one, Macro PCS. Only one of you has ever heard it. They were actually kind of sold, or they fused with T-Mobile USA in 2012 or a little bit later. So we know where exactly this the eNodeB comes from. Yet again, if we actually had a client certificate, that would be probably the most awesome combination. Then, we found a few little interesting things. The classical passwd command for changing a password. We've got shallow user and we've got RBS, and we actually just wanted to change a password just to play around with it. And actually it turned out that if you change the password for RBS, also the password for shallow user will be changed, and the other way around. So for some reason they actually combined the passwords for both user accounts, somehow magically even for passwd. So it looked a little bit strange. Then, as Hendrik already said, we've got quite old SSH, so we actually had to go in for our old Diffie-Hellman group 1 SHA-1. Modern SSH simply won't do this anymore, so we had to re-enable it. Then when you're on the box, interesting, you had something that was called cell and UE traces. Sadly, we only had cell traces, so basically you can see status and log information of the cell that actually was on the eNodeB and a few neighboring cells. From the documentation and the info that we found, if we would have had a UE trace, this UE trace actually logs everything that a mobile device in the LTE cell does over a certain amount of time. So, if you have access to an eNodeB in the field, you just kick in the UE trace command and you basically log all unencrypted information that goes through that mobile device. So, rather nice for playing around with. Then, yes, when you do stuff, you always find really, really, really strange things. So, all communication that you've seen so far went into private IP address space, which is the way that you do it in your own network. Now, we found a GOP remote session that was actually trying to find a server to a public IP address. We were able to have it connecting to us, so you've got basic GOP communication, which you could attack, but if anybody of you knows the nature of GOP, you need quite a lot of information to actually be able to push objects over the line until something happens. So, as it was the only public IP address, we had a closer look at it. And I've got to say, the next slide it's vague. We can't guarantee for any correctness on the next slide, but what you do, you've got an IP address, you look it up, and you remember Macro PCS. The IP address that we found actually belongs to an Iranian cellular operator. So, we can't guarantee that basically the American telco simply misused a public IP address, but you've got to admit it simply looks very, very strange. And time-wise, if you go down to it, the address space was actually registered in 2012. And we know from the log files that the eNodeB was up and running in the field up to 2013. So, for what reason is this American eNodeB actually talking to the network of an Iranian operator? It's strange, it doesn't make any sense. So, as said, the information is vague. We've just got the data that we got of the eNodeB. We've got no idea if maybe the IP address space was, shared or something like that, or as said, a misused public IP address. But stuff like that actually just is scary. And we have to say the port that it connected to, on the Iranian IP address nowadays is down. So whatever was running there isn't there anymore. So yeah, you know, a little bit of scary shit in telco networks.
So, okay, so first, that was our first start with our research we wanted to present for you. You really see that there is no magic behind, as the log file already says. It's just a easy system with some special characters, I would say. It's also very strange that most of the devices have that the config is still not erased. We also bought a second blade for that RBS just while we are here. That one is from T-Mobile and it looks exactly like the same. That is quite interesting to do a lot of stuff. We now also have access to the binaries, which is some future work for us. So we are taking a look to that. But basically, the attack vectors for such devices are based on that signaling, so you can just access that management or control traffic there to do some traces of UEs, to establish connections on your own, or also hand over. There is no security in reality, and sometimes there is no security, so that IPsec stuff, or even if you are able to extract it somehow. For example, like that OAM, and what we've seen there is not really good. So that's an architectural problem, I think, or a hardening problem. So that is development, hopefully the vendors are working on. But that is a quite new device, or quite new, 2012. It's an LTE device, which is out in the field. So we expect that there are a lot of base stations out there which are exactly configured like that. And if signaling and ORM is not working, even then, with having physical access to the device, you can just get that flash disk, that compact flash, and put into your laptop, extract all necessary information, like the password file, like that IPsec information, and then you're in again. So there is a lot to do. Good. That's it so far. That is what we wanted to present to you this time. Thank you. If there are any questions, let me know.